So in this topic, what I am covering is the representation of the binary tree. That is how you are going to represent the binary tree. So binary tree, when I am going to talk about binary tree, I will be talking mostly about strict binary tree, because that becomes useful. The strict binary tree is more useful, and that is why we are finding the formulas, right? These are the generalized formula for strict MRA binary tree. So I will be, when I will say binary tree, it will be like strict binary tree. Okay, how do you represent? First of all, what you have, that you can represent anything, like what you have. So you usually, what you will be having is array or linked list. Linked list, these are, these store the a set of values, right? So by using these two things, you can store the elements of the binary tree, and you'll be having doubts that how, by using array, how can we store the binary tree, right? So it is so much simple. And but in this playlist, you would find the binary tree created even in program, or everything I will be creating using linked list, but not using array. But for idea, but I can give you the idea of how we can use this array to create binary tree. Imagine I have a tree like this. So let me reduce the size, right? This is a root node. So root node is, let me take it as A. Then let its parent children be BC, then D, E, then G. So now I will represent them in array. So it is so much simple. The first one is A. You go level by level. This level you went. Now you go to this level. There is B. Now C. Now D. Now what? Now E. Now F. Now G. Right? Have this array. So I have represented the binary tree in array. But the most important thing in binary tree is the relation, right? What are, like, B is a child of A. That is my intention. That is what important for me. More than this data, I should know what is the relation between these nodes. But you have not stored it in this array. So what you can do is, I will go by one indexing, one based indexing, not zero based indexing. So let me, I will, you will get to know why I am not using zero based indexing. Imagine this is null. So 1, 2, 3, 4, 5, 6, 7. These are the indexes, right? So let me draw some line to differentiate. So let me take the elements here, elements in this elements, it will be here. Those elements are what? A, B, C, D, E, F, G, right? E, F, G. Then what are their index? What are their index? Index is, for A, it is at 1, B is at 2, then again 3, 4, 5, F is at 6, G at 7, right? You can see here, G at 7, F is at 6, E is at 5, so it goes on. Now, so A is parent of what? It is parent of, A is parent of B and C, right? So what is a left child of A? That is B. So for B, A is a left child. So what are they? What are their relation here? It is nothing but 2i, right? If A is at I, its left child will be at 2i, right? Again, if you have doubt, let us see again. Let us see relation between D and B. D is a left child of B, right? Right? D is what? It is a left child of B. So what is the relation between their indexes? So it is 2i. If I is 2, then its left child will be at 2i, means at 4 it will there will be. So again, if you have again doubt, you can check for C and F. So C is at index 3. So if node is at index 3, its left child should be at 2i, that means at 6, right? So come to 6 and see, you have 5, F. So what is F? F is a left child of C. So that is how the relation goes. So for if you need the left child, go to 2i. So similarly, let's see for right child, right? For right child, let me see. So here C is the right child of A. C is the right child of A. So its relation is 2i plus 1. So if I is equal to 1, then if you substitute this formula, you will get 3. So that means you will, this is the formula. So if I is the node, then its right child will be at 2i plus 1. Go to 2i plus 1 index, you will get C, then that return that is what the right child. So if you have doubt, check now with C and G. So C is at where? It is at 3. So I will do 2i plus 1. So I is where? Well, it is 3. 3 to the what? 6. 6 plus 1 was what? 7. So go to index 7. What is there? G. So G is what? G is a right child of C. So this formula holds good. So if you need right child, if you are, first of all, you are in index I, then go to 2i in order to get left child. Go to index 2i plus 1 in order to get right child. This is left child, this is right child. So this is about array, use binary tree using array. So this is over. Now let us go to linked list. Again, I will have what? I will have, so if I am standing here, what are the information I need to store? So obviously I need to store the data of this node, and I need to store left child address, right? I need to store left child address, or you can say you should store a pointer that will point to the address of left child, right? It is so much logical. So I will again I need to store another pointer which points to the address of right child. So you need 3 things. If you need 3 things under a single name, as I said, you need structure, struct struct node, and what it will have? It will have again data, and it should have a pointer of node type, and it is, I will call it as a left child, L child, child, and then node again of node type. I will take a pointer of right child. So I have explained you why data and left and right child is needed. So this is a structure for me. So when I create a node, then how the node will look like? So node will be looking like this. So what is that is linked list node will be looking like this. So here we will have data. Let us take 10. So this left child will be pointing where? It will be pointing to the left child, right? It will be pointing to left child. Imagine let's take left child has a data 1, right? Again, this will be pointing to another node, right? That is the right child. Imagine the data is 2. So again, further this will be pointing somewhere, and this will be pointing somewhere. This will be pointing somewhere. So imagine I will take again node. I will create node, and this will be pointing here. Let me write somewhat smaller. So I have here, then this will be pointing say here, and this will be pointing here. So now you'll have one question. Here I will store again like 3, 4, any values I will store here. Let me say 5. Let me store 6. So now this node will be in this node, the left child, that is this left child will be pointing this to this entire node. So again right will be pointing to the center node. So further after that, again left and right, again we created a node. So imagine After this I have no node at all. Then what you will do, you make it as a null. So you make it as a null. So if there is nothing after this, you can make it as a null. Okay, now you will have again, let me show you another formula. That is how many null pointer you will have. Here in this case you have 8 null pointers, 1 2 3 4 5 6 7 8. So how many nodes you have? You have 7 nodes. So if what is the relation between number of nodes will be equal to 8, that is number of nodes, number of node will be what? It will be equal to number of null pointers. Null pointers I am telling you, null ptr minus 1, right? So this is the formula. Again, this is strict binary tree what I am talking about. So this is how you represent using linked list and array. In next video I will be talking about comparison between full, complete binary tree, or strict, full and complete binary tree. All three difference I will show you. So thank you for watching this video.